Okay, so welcome back to the hybrid mode origin seminar. Today we have a speaker from Alien Earth Biology team, Fred Ciesla from University of Chicago. But Fred was here actually as a graduate student and got a PhD at University of Arizona from RPL. So I'm very happy to see him. So Fred, take the floor.
All right. Thank you, Serena. Thank you for inviting me. It's good to see a lot of familiar names on the participant list. Good to see everybody. Hope you're all doing well after these last 2 years. What I'm going to be doing today is talking about some papers that came out last year that I was a part of. And basically the reason why I picked this was, number one, because I almost forgot I had to give a talk, and so wanted to pick something that was easy, to talk about. But also because I've been thinking a lot about this issue of what does it mean to have a possibly habitable planet? What are the key ingredients that are necessary? And by that, not only what are the ingredients, what does that mean in terms of the processes that have to be at work in order to create a potentially habitable planet? So we've been focusing a lot on carbon lately because while we tend to think of a habitable planet as something that occupies the habitable zone around a star, we are carbon-based life forms. And so we do think carbon is an important ingredient as well in terms of constructing a habitable life, so a habitable planet. So what I'm going to do quickly is hide all these unnecessary Zoom windows and then start the talk. There we go. All right. So yeah, as Serena said, please feel free to interrupt at any time if folks have questions. I'm happy to make this more of a conversational thing. As I said, I'll be talking about some work that's been done and has come out, and I just want to highlight the people who I've worked with on this. These are my 4 collaborators on the 2 papers that I'm going to talk about. It's been a really fun team to work with because we all bring a different kind of perspective and expertise to this collaboration. Jackie and Mark are both geochemists, specifically mineral physicists, looking at the interior composition of the Earth, both in terms of the mantle composition as well as the core. Ted Bergen and Jeff Blake are astronomers, astrochemists, looking at star-forming regions and protoplanetary disks and trying to infer what the compositions are of areas where we think planet formation is taking place. And my job is to kind of run in between, finding a way to link the planetary and astronomical view. This has been a really fun collaboration to be part of. It's one of those things that, science in the before times when we could get together and chat and exchange ideas. Fortunately, that translated pretty well over Zoom for us. And so we were able to keep some of that excitement and enthusiasm for the work going even during the pandemic. So I'm very pleased about that. What I'm going to specifically be talking about are these 2 papers that we published last year. One in Science Advances, Jackie Lee was the lead author on it, looking at Earth's carbon inventory, and I'll get more into that in just a moment. And then work that Mark led, looking at the volatile depletion, specifically looking at the carbon and sulfur systematics of iron meteorite parent bodies and how that may play a role in setting the carbon inventory of the Earth. And so for those who are interested in what I'm talking about, or for those who can't understand what this talk is about, I recommend you can take a look at those papers, and we go into a lot of detail there, more so than I'm going to be able to do justice for today. But to set the framework, I always like this pick this image as something to start with, just kind of thinking about the processes and different stages that we're thinking about when it comes to planet formation, starting off with a molecular cloud of dust and gas. In our case, something that was floating around in space and probably contributed to by maybe something on the order of 50 or 60 stars that have exploded and ejected material into a cloud that eventually collapsed to form a star, and due to angular momentum conservation, a disk around it. In fact, a lot of the mass from the cloud probably went into the disk first and fed into the star through that pathway. And what's important there is it means that the star and the disk are made out of the same collection of materials. So compositionally, we expect them to be tied together, and the composition of one in general is going to reflect the other. Now, once you start with this this star and the disk around it, we call this a protoplanetary disk because this is where the raw materials that contain planets are contained. And so the processes in there dictate how the planets came together and what their compositions were. There's a lot of interactions between the dust grains, the dust and the gas, the dust grains colliding, sticking, significant amounts of transport, processes that we continue to study and try to understand in detail, both in our solar system as well as disks around other stars. But what we generally accept as having taken place is that the solids within the disk collide, they hit, stick, and grow through a variety of processes, sometimes through dynamical interactions with the gas as well, but leading to larger and larger objects that eventually become planetesimals, the building blocks for the planets themselves. And the gas from the disk dissipates over a period of millions of years. And after that's gone, it leaves you with a relatively well-ordered planetary system. And so the properties of that planetary system are set by the integrated evolution that occurs through all of these different stages. And so what we want to try and do is be able to look at different things in our solar system and beyond as a way of filling in the details, as I was saying, in terms of understanding the timing of events, how they worked in one region of the disk versus the other, how they worked in our solar system, and how they may compare to those processes that were operating around other stars. Now, there are different ways that we go about studying these processes. I'm not going to get into all of the details here. I want to focus on the compositional studies, though. And one of the key things that we use in our solar system in terms of understanding what the building blocks of the planets were and what the processes that took place in those early stages of planet evolution are by looking at meteorites. And so this is an example of a meteorite. This is a slice of the Allende meteorite, perhaps the most well-studied rock in existence. It fell to Earth in 1969, right as we were getting ready for return samples from the Apollo mission. Significant mass of this fell in the Mexican desert. And so a lot of it was available for people to study and use brand new instrumentation to be able to pick apart the rocks, understand what their compositions were, and try to tell a story of what they were telling us about the formation of our solar system. These chondritic meteorites in particular are really useful because these things never underwent differentiation in their parent bodies. That is, we know the Earth, and I'm going to come back to this, has a metal core at its center and is surrounded by a silicate mantle. And that's because the Earth was hot enough early in its history that it became molten, and there was a separation of the more dense iron metal and the less dense silicate mantle into these different structures. Chondritic meteorites never underwent these, unlike, say, their iron meteorite brethren, who are coming from samples of planetesimals or bodies that got hot enough and melt and differentiate in the same way that the Earth did. The fact that chondritic meteorites did not do that, and in fact, the metal and the silicates are well mixed in here, is telling us that these are providing us records of the dust grains that were floating around in our solar nebula, the protoplanetary disk, which circled our sun after its formation. So these are very exciting and interesting samples because they're telling us about that collection of dust that came together. And basically that dust has escaped any of the baking that would have erased significant information about their formation history. So we try to pick these apart to learn more about that dust that was floating around in our protoplanetary disk. Now, alternatively, what we can do is take the astronomical perspective and point a telescope at one of the objects that we're interested in and use spectroscopy to determine their chemical compositions. And so there's lots of ways that can be done. And I'm just showing an example here of a spectrum of the sun. And what you can see are absorption features, these black lines at particular wavelengths, which are telling us about the atoms or molecules that light is passing through. And so we can do this as a way of learning the compositions of many things. In this case, we're learning about the composition of the sun. And what's important here is that what it allows us to do is make a comparison between the composition of what's in the sun and the composition of the things that went into forming the solid objects in our solar system, the solid building blocks for planets, and understand their relationship. And so that's done in this plot here, which is basically showing you the abundances of all the elements in the periodic table for the most part, in terms of their abundance in the sun, which is on the x-axis here. Notice this is a logarithmic scale. And it's normalized, I believe it's to silicon here at being 10 to the 6 atoms of silicon. So what you're looking at here, for example, in terms of uranium, there's 10 to the minus 2 atoms of uranium for every 1 million silicon atoms in the sun. And so we can learn the solar abundance through these spectroscopic studies, and we can learn what the relative abundances in chondritic meteorites are by taking these samples to the laboratory, picking them apart, measuring their atoms. And what we find is this really strong one-to-one correlation between the abundances of elements in the meteorites and their abundances in the sun, which is consistent with what we had described earlier, in that saying that the sun and the protoplanetary disk from which the planets were formed were going to be made out of the same materials. They were made from the same mixes of elements. Now you can see there's a couple exceptions here. Lithium is more abundant in chondritic meteorites relative to silicon than it is in the sun. And we know that because lithium burns up early on during the star's early evolution. And in the upper right here, you can see oxygen, carbon, and nitrogen are more abundant relatively in the sun than they are in chondritic meteorites. And that's because these elements in particular are very volatile, and they don't necessarily form solid materials unless the molecules that they're contained in reach very, very low temperatures. And that's an important part of what we're going to be talking about. But for the most part, we can do this. We can compare what we're seeing in the sun to what the potential building blocks of the planets are. And we find that, there's a very good one-to-one correlation. The chondritic meteorites are basically made out of the same stuff as the sun, with only a few exceptions. And the way that people have thought about this for a long time, early on at least, is to think about, given the conditions that we expect in the protoplanetary disk, what are the solids that we expect to form? And this has guided our view, kind of our discussions for how different things would form or be available to planets for a long time. And so for a protoplanetary disk, we expected this to largely be made out of hydrogen with some helium, with a small smattering of more of heavier elements throughout. And what people have done is they've tried to understand, given the temperatures and pressures that would exist in the solar nebula, what solids do we expect to have been present to seed or be the building blocks of the planets? And so one of the ways that we can go about doing this is using equilibrium chemistry. And this is what's been done, or was the primary tool decades ago. And just an example of what you might do is you might be interested in when sulfur condenses. When does sulfur actually go into the solid phase? And so this is the standard reaction that we look at in terms of when sulfur actually becomes available as a solid. You have iron solid, iron metal, reacting with hydrogen sulfide gas, and that yields troilate, FeS, as a solid with some remaining hydrogen. And so that's what we could write similar equations for basically every single element, trying to understand what are the reactions that would lead to different solids being available. We can look up the equilibrium constant for this reaction based on thermodynamic equilibrium and write it in terms of the activity of the solids, which is the A factors here, and the pressures of the corresponding gaseous species in this reaction. The important thing to note here is that this relationship, the equilibrium constant here, is a function of temperature. So depending on the temperature, you're going to have a different value. And obviously your pressures are going to be part of this story here, meaning that for any, again, the fact that you can do this for any element is telling you that, what's available as a solid is going to be dependent on the pressure of the system, the partial pressure of the species that are there, as well as the temperature. And so, as I said, this is something that's been done for decades. This is actually taken, this plot here is taken from work that John Lewis did back in the early 70s, applying this idea to try and make sense of what the bulk compositions of the planets were. Now, the idea is that for a given temperature and given pressure, what you can do is, again, taking all the elements in the periodic table, writing their potential reactions and solving for it, you can figure out when things will start to condense from the gas. And so what you can imagine is, imagine starting off very high in temperature, about 2000 K, and everything there will be so hot that things will be gaseous. But if you stay at a fixed pressure and just cool over time, what will happen is you will no longer just have gas present, but you'll cross the stability field for different species. So the first one in this particular plot that you would cross would be perovskite, a mineral that is, as I'll show in a minute, something that we find in meteorites. As you get lower and lower, you cross the iron stability point. So at temperatures above this curve, iron exists as a gas. Below this curve, iron exists as a solid. And then you can see here, this horizontal line represents when the iron sulfide begins to form. So at a temperature of about 700 Kelvin or so, you would start to have this reaction where the sulfur would react with the iron and become incorporated in the solids, and therefore be available to be incorporated into any solids that were present. And so this is something that's guided our thinking, for better or worse, for a long period of time in terms of understanding the chemistry of materials in our solar system, as well as what we expect to be available for planets in other protoplanetary disks. Now, I say for better or worse, and I mean nothing bad by that, but I'm going to show you how it translates to and may have affected how we've thought about some things, particularly when it comes to carbon, and some of the revisions that we think are necessary in terms of thinking about that. But there's reasons why this has been so successful. This is so well used in the literature, or popular, I should say. This is a plot from Grossman and Larimer in 1974, doing exactly that calculation that I talked about earlier, now showing you a bunch more elements, showing you the temperature on the x-axis here and the fraction of a given element that's condensed on the y-axis. And so you can see, for example, again, starting off at, say, 2000 Kelvin, and this is for a fixed pressure. This is a total pressure of 10 to the minus 4 atmospheres. Everything starts out in the gas phase, and as you start to cool off, the first thing to condense and form a solid is osmium here. So osmium is in the gas phase at high temperatures. Lower temperatures, it's in the solid phase. You got different other elements here. I'm going to just focus on a few main ones. Aluminum here is an important one that I'll be talking about in just a moment. It condenses as Al2O3, so it reacts with a little bit of oxygen. But this is where we expect essentially most of the aluminum to reside when it first condenses. And you can see that we kind of can define a characteristic temperature at which this happens due to the steepness of this curve. This is basically, again, plotting the fraction of aluminum that's condensed. You can see that, that it starts condensing at about just under 1700 K. And about, if you go vertically on here, you get to about 50% of the condensation temperature in a very small, or 50% of it condensed in a very small temperature range. The last 50% may take a few tens of Kelvin to cool before it's completely condensed, but you can see it's pretty easy to associate a characteristic temperature with these different reactions. And so this is often what we refer to as the half or 50% condensation point, is the temperature at which 50% of the element is condensed or existing as a solid. Now the question is, should we believe this? And I've talked about why this is something that people have used. Is there any merit to this? And certainly there is. And so what I'm showing is a different version of the same condensation calculation, focusing at high temperatures, this is taken from a paper by Andy Davis and Frank Richter, a review chapter from 2005. And the way to read this is, again, temperature is on the x-axis in Kelvin. And this is just showing you how much mass is going to be condensed at different temperatures from a gas of solar composition and how it changes with temperature. So again, if you start out at really high temperatures, there's nothing in this plot, say, solid above 1750 Kelvin. But what you're looking at here now is the fraction of solids that are condensed in terms of that chondritic composition that I showed you before. And let me just talk through this a little bit to explain it in detail. So at high temperatures, only a small amount of solids begin to condense, and we're showing the main main minerals that would form here. The first thing that would form would be this aluminum oxide, corundum, Al2O3. It makes up, on the y-axis, just less than 1% of the solid composition that we would expect to eventually form if everything condensed out. But the first things to form will be these aluminum oxides. As we go to a little bit lower temperature, we get minerals called perovskite, hibonite, spinel. You can see that they're common, or what they have in common is they all contain calcium and aluminum mixed in with some oxygen, some titanium that also condenses at these high temperatures. But these are the species or the minerals that we expect to form at these high temperatures. Now, as you go to lower temperatures, around 1400 K or so at this particular pressure, you start getting magnesium silicates and iron metal, the more dominant, more massive contributions to solids that eventually form and make up the solid composition of the planetesimals that we're interested in. But note that we still have the calcium and aluminum have already condensed out. It's just the minerals that we're expecting them to be contained in changes depending on the temperature that we're looking at. But it's important to note that perovskite, corundum, hibonite, spinel, these are the minerals that are expected to first form in our solar system and at these high temperatures. And the reason why that's important is we can look to the meteorites again and try and understand whether or not there's any matching between what we see in the meteorites and what ultimately, what these calculations predicted. And so these chondritic meteorites, as I said, are collections of dust particles that were floating around the solar nebula. Each one of these things has a different story to tell, but what I want to focus on are these white kind of oblong inclusions here, because these are examples of what we call calcium aluminum rich inclusions. And so as their name implies, they are calcium and aluminum rich minerals, largely oxides. And they are thought, based on our radiometric age dating, they are the oldest dated objects found in our solar system, predating some of the materials that they're embedded with by millions of years. So these chondrules and the matrix grains that you see here scattered about they're all mixed together on the scale of centimeters, millimeters type of thing that you can form in your hand, hold in your hand. But these CAIs appear to be for as best we can tell, are the oldest objects in our solar system. They're calcium and they're aluminum rich minerals. And in fact, if we do a close-up and look at the minerals that are found in these things, the minerals that we find are minerals like spinel, hibonite, perovskite, diopside, things that we know and recognize as being both calcium and aluminum rich minerals, but also exactly these minerals that were predicted to have formed at these high temperatures. So this has been taken as hint that this equilibrium chemistry played a role in shaping the minerals that were going to form in the solar system and what was available, because we do have a matching of these very high temperature minerals with exactly those objects that are found in our found in these meteorites. So those CAIs are thought to have formed very early in the solar system history when the disk was very hot, because those are the minerals, the temperatures that are required to form these minerals. Note that if you only heated it to 1000 Kelvin or something, you'd get different aluminum and calcium minerals. You wouldn't get perovskite, hibonite, or corundum based on these calculations. So that's why this has been used as a tool for interpreting what we see in the solids in protoplanetary disks as well as planets, because they tell us there seems to be some matching. This equilibrium chemistry has guided what the system wants to evolve towards. Now, the fact that we see hibonite and corundum in these meteorites also tells us that equilibrium chemistry did not rule the entire day. Because note that corundum only is stable in these calculations at very high temperatures. But we have corundum in those meteorites, despite the fact that we're holding them at much lower temperatures. So even though we formed corundum, which is consistent with these equilibrium calculations, the fact that corundum survived in that the aluminum didn't go into another mineral as the system cooled also tells us that equilibrium did not completely rule the day. And there were other factors at play that were dictating how these solids would have formed. I'm just going to pause for a moment to see if there are any questions on anything so far. I can't really see. So if you have a question, please feel free to shout out.
Has a question. I think Maitri can, if you don't mind, Fred, Maitri can probably speak up.
Yeah, please go right ahead, Maitri.
Okay, I hope you can understand. I have a bad cold, but anyway, so the question I had for you was, at temperatures above, say, 1500 Kelvin, what's the speciation of aluminum or calcium or titanium in the gas phase? I mean, are they present as oxides, or are they, what would you?
That's a great question, and I don't know off the top of my head, but I should know that. I mean,
no problem.
Yeah,
I'm curious. Yeah,
we can look that up, and I can get back to you on that.
Okay, sounds good.
Any other questions, or should I continue? All right, I'll keep on going. But as I said, feel free to interrupt at any point. Oops. All right, so again, this has been the framework that we've used for understanding when do we expect these different elements in the periodic table to be available, and at what abundance do we expect them to be available when we're assembling planets. When we're at very high temperatures, we start to get the magnesium, silicon, iron, these main elements here, and they serve as kind of the main massive objects that come to in terms of assembling planets. But if we were interested in different elements, all we'd have to do is understand their thermodynamics, and we can make predictions at what temperatures do we expect them to be available in order to be incorporated into the solid planets. Because ultimately that's what we're trying to understand, is how do these things come together to form, say, the Earth or another potentially habitable planet. Now, the good thing is we can actually do a similar thing with the Earth in terms of trying to understand what is its bulk composition. And we can do that through a variety of ways. But sitting here on Earth, we have a lot of ways of collecting information about what the Earth is made out of. You know, we can collect samples of mantle rocks, things that have erupted on the surface, or old rocks. We can take seismic studies of the Earth's interior, understand where we expect there to be solids or liquids or different density regions. We can look at meteorites and make inferences about what the composition should be if everything was present as in a solar abundance. And so people have done this in a lot of ways, trying to create and understand what is the bulk composition of the Earth itself, and then how does that compare to the meteorites or to the sun. But the Earth is much more complicated. The Earth has been geophysically active for 4.5 billion years, and not all of it is accessible to us. You know, we expect the Earth to have been created out of the accretion of things like meteorites, and it's important to note that meteorites come in a lot of different forms, not just the chondrite that I showed you above. But because the Earth is geophysically active, that allows for these elements to move around once they're incorporated into the Earth. And so we can't go down and collect material from the core and understand what the composition of the core is. We have to rely on indirect methods in terms of, as I said, seismic studies or different inferences that people make. Even in the mantle, even though that's more accessible, we can only make constrained arguments about what the bulk composition is. And so there's lots of people who have worked to define what the composition of the Earth is. And for the most part, what we do is we focus on the bulk silicate Earth, because that's where the measurements provide the most guidance. And so what we tend to think of in terms of what I'm going to refer to as the bulk silicate Earth is everything with the Earth except for the core. And so people have spent a lot of time constraining what the mantle is made out of, understanding that some of the elements, because of their chemistry, they're what we call siderophile, meaning that they like to go into the core. They like to be in metal as opposed to rock. There's going to be some evolution there. So I will say that it comes down to some tricks and some arguments, and different people who will apply different approaches and get slightly different answers. But the trends that I'm going to talk about today, or the trend that I'm going to be talking about today, is robust. And while numbers are going to be model dependent, it does seem, like I said, we're talking about differences at about the 10% level. So even if the numbers on the plots don't line up with one study to the next, the story that I'm going to be saying is general enough that we can still have some confidence in it. And what's important and what's interesting is when we look at the bulk composition of the Earth, is it gets really complicated. Now, what I'm doing here, or I've taken this from a figure from Wood 2011, but what's done here is we basically plotted the abundance of different elements as a function of their condensation temperature, the temperature at which they would form solids in the protoplanetary disk. Now, these are all normalized relative to the most refractory elements. Those are the ones that form solids at highest temperature, and relative to what we see in chondritic meteorites. So if everything plotted at a value of 1 here, that would mean that the Earth had the same exact composition as the chondritic meteorites. We immediately see that that's not the case. And there's 2 different effects that are important here. First, remember that what this plot is showing you is the outer portion of the Earth, the bulk silicate Earth. And we're not showing you, we're not taking into account the composition of the core. And that's why you see some of these elements like gold, palladium, rhenium, osmium, tungsten, elements that are siderophile, they're depleted relative in the bulk silicate Earth compared to meteorites, because these elements prefer to go into the core. It doesn't mean that the entire Earth is missing these elements compared to the bulk meteorite, rather just the outer portion of the Earth. And that's why they're so rare on the surface of the Earth, because the greatest inventory is probably contained in the Earth's core. And so that's why you can see, particularly at these high temperatures, a significant difference in their abundance. Aluminum doesn't want to go into the core. Calcium, these are lithophile elements. They want to be in rock, and so they're going to stay in the mantle. Now, another important thing to know is that as we go to lower temperatures here, lower condensation temperatures, regardless of whether they're siderophile or lithophile, what we see is there's a decrease in their abundance relative to meteorites. And this is called the volatile element depletion trend. And we don't have an exact understanding of why this happens. It is robust, however. We see it again in all the estimates for the bulk silicate Earth. Basically, the trend is as you have increasing volatility, meaning that the elements condense at lower and lower temperatures in a protoplanetary disk, the less abundant that meteorite or that element is in the Earth relative to what we see in the sun or in meteorites. Now, some of these things, you have the siderophile aspect, the core formation certainly plays a role. But again, this is independent of lithophile or siderophile, meaning that you still have this decreasing trend in abundance as a function of temperature. Is there a question? No? All right. This is another plot showing the same thing. I'm sorry that no one has agreed universally whether temperature should increase or decrease on the x-axis. So you might see this flip around a little bit. But this is more elements labeled, again, showing this trend of basically things are, we're above 1 here just because we're normalized to a different element. But basically we have, again, a flat abundance at high temperature, except for those siderophile elements. So presumably, if we had all of the Earth's tungsten mixed in, including what's in the core, it would be plot up here as well. But again, we go to lower and lower temperatures, we see that the elements become more and more depleted. And so this is really interesting because when we look at carbon, carbon has a very low condensation temperature. Typically, depending on what you assume it's contained in, under equilibrium conditions, carbon is expected to be either in methane at these low temperatures, or we think that it may be hard for CO to be converted to methane in a protoplanetary disk, and it may stay locked in as carbon monoxide, which is what it would form at higher temperatures. Regardless, both of those molecules have very low condensation temperatures, and so it makes sense that following this trend, carbon is significantly depleted relative to all these other elements. Now, this is important because what we're interested in terms of carbon for the Earth is if we want to form life, we want that carbon to be available at the surface so it can take part in the different chemical reactions that are going to be important in giving way to life. And so, the fact that it's so low in abundance in the Earth raises the question of, are we dangerously low in carbon, or is there plenty enough carbon in the Earth's budget for those life-forming reactions to be important? The other important thing to note is that carbon actually is siderophile. And so carbon actually wants to go into the Earth's core. And in fact, most of the Earth's carbon is probably contained in the core, which would mean that unlike tungsten, which if you added all the core, everything that we have in the core, it would bring you back to this volatility trend. If there's a lot of carbon in the Earth's core, then since this is what's in the bulk silicate Earth, it would move you up here and completely disrupt this volatility trend. So carbon's behaving a little bit different, and we want to understand why. And so that's something that we've been focused on, because again, if we're forming if carbon is so depleted on the Earth, we want to understand, would these, whatever process led to its depletion, have played a role in limiting or giving lots of carbon to another potentially habitable planet. So we wanted to spend some time on carbon.
Fred, I would have a question.
Yeah, go for it.
Yeah, just a simple question. So you basically show the condensation sequence as a function of temperature, assuming a constant pressure. I was wondering that if, I'm sure it was probably excluded, but if one would allow for both the temperature and pressure to change, could one get better, match to abundances?
Yeah, people have done that. You can do that. In terms of the carbon story, the answer is no. But you can't. I mean, you can map out in pressure and temperature space what would condense out at any given time and compare that. And that's part of what John Lewis did. And Daniel, I know you were missing the beginning of the talk, but just showing a calculation from a while ago following a pressure temperature history through such a calculation.
Okay, thanks.
Yeah. And so the reason why this is important, and I realize that this is going a lot more slowly than I expected, so I apologize. When we talk about the Earth and wanting to get carbon into it, if we follow this equilibrium story, as I said, most of the carbon would either be as methane or carbon monoxide, which in a protoplanetary disk would only freeze out as solids at very large, very low temperatures, very great distances from the star. Much further beyond the water snow line that we often talk about in terms of setting planetary compositions. We know the Earth only accreted a little bit of water, and it probably has something to do, this is an old simulation, but it has something to do with radial mixing and planetesimals from one region of the solar nebula being scattered inwards to be accreted by a growing Earth. And so if the Earth only has a small amount of water, that suggests only a small amount of material from beyond the water snow line came in. And if we are trying to source material that's rich in carbon, we have to sample from much further out. So it would be a challenge dynamically to do that. So we wouldn't expect a lot of carbon to be delivered in this way. So the question is, are we thinking about this correctly? And so what we started doing was looking at the carbon inventory of different things in the solar system and comparing that to one another. And so this is just a plot. This is taken from a paper by Ted Berg and myself and my collaborators from 2015, looking at the carbon to silicon ratio in different objects in our solar system, as well as in the ISM. And we find, that the sun and the interstellar medium have roughly the same carbon to silicon ratio. Comets seem to have, if you add both the dust and gas from Halley, have the same carbon to silicon ratio. As we go to more rocky objects, the carbonaceous chondrites, the ordinary chondrites, andesite chondrites, and then the Earth, we have this depletion of carbon relative to silicon. And so this isn't just something that happened on the Earth. This is something that happened in terms of removing carbon, or at least making carbon only partially available to what we consider possible building blocks of the planets. And so the question is, what set that carbon inventory? And then what does that mean in terms of the Earth's low abundance here? And so I've just shown some of the carbon to silicon ratios here. We have different types of meteorites, and the most abundant carbon to silicon ratio, the highest abundance is about 1. So even the meteorites themselves are depleted in carbon relative to the sun. So there's something that's limiting the amount of carbon that's present in the sun, in these rocky objects. And so the question is, what happens with carbon? We started off in the interstellar medium, as I said, with carbon in a lot of different volatile forms. Now, equilibrium chemistry doesn't rule the day in the interstellar medium, so there's lots of things, that molecules that exist that are not predicted by equilibrium. But the dominant carriers were thought for a while to be CO, carbon monoxide, methane, etc. These kind of volatile ices. And we can see spectroscopically that they're, in hot cores and stuff, that such molecules do exist. The idea in equilibrium chemistry is that this would all have gotten added to the disk, vaporized, and then form new species. But the question is, what if that doesn't happen? What if we inherit this directly without vaporizing everything to begin with? What then occurs? And with carbon, it's important to understand not only what are the icy species that are present, but what else happens, excuse me, to these carbon carriers, particularly in the ISM. As I said, these are not places where equilibrium chemistry rules the day, but other things can be happening. And laboratory studies have shown that if you take these simple carbon ices and water ice, mix them together in an interstellar environment, and then bombard them with ultraviolet photons like what we expect to occur in interstellar space, you drive disequilibrium chemistry and take these simple ices and produce more refractory organics. And so more complex species, different carbon carriers. And so what's brought into the solar system from the interstellar medium is not just these ices that we identified before, but there's also about 50% of the carbon is contained in these refractory organics. And I use refractory here. It's important because remember, we talked about these as being volatile ices, but the organics, these other species that form from these disequilibrium reactions, are going to be much higher, stable at higher temperatures. And when we look at the carbon that's contained in, say, the chondritic chondrites, and what we find is a lot of that carbon is in organics. So we think there may be a connection here. So in this story of forming a disk or forming a system, what we have are these volatile ices coming in along with the refractory organics. And what I'm showing here are the temperatures at which these different species would vaporize. Now, in equilibrium chemistry and that condensation calculation, what we were doing was starting off hot and then cooling off. And so we predicted that under equilibrium, carbon would only exist as a solid down at 40K or so, because that's what equilibrium chemistry had suggested. But if we're taking these things and bringing them into the disk without vaporizing them, these carbon carriers can survive to a variety of temperatures, well beyond just those simple ices, now that we have these refractory organics contained within them. And so this is important because we started thinking about what happens with these carbon species as they mix around in the solar nebula and in a protoplanetary disk. And so we typically think of these kinds of transitions in a disk as being the snow line or evaporation front. And water is something that's been studied a lot because that's obviously a significant molecule in the solar system. And in the water snow line, what would happen is you'd have water ice in the outer disk, water vapor in the inner disk. When water ice crosses the snow line, it vaporizes, becomes water vapor. That water vapor can cross the snow line again, freeze out as water ice. And you can go through this process of cycling things through different phases. And you can lead to a pileup of water at this location, but limits essentially, again, that solid material as existing only outside this evaporation front or snow line. Well, with carbon, if we're doing this inheritance as opposed to this evaporation, what we have then is a significant number of transition points where solids will lose a little bit of carbon depending on their temperature. So if we have an interstellar medium inherited material and it drifts inward and crosses the CO snow line, it would vaporize. If it crosses, that CO would vaporize, then lose methane, then carbon dioxide, then methanol. And then eventually you would cross this 500K region where those refractory organics would start to vaporize. But what's important is remember that these are not equilibrium products like the water example was. So what would happen in the outer disk is you might lose some CO to the gas phase, but then that CO can cross the CO snow line again, freeze out again, and you're going to maintain your total inventory of CO through these processes. That doesn't happen when you destroy these refractory organics. What happens instead is that these refractory organics, when they heat up, they decompose, forming things like methane, CO, and other stuff, things that don't freeze out anywhere near this inner star, in the inner solar system, only where these low temperatures are reached. So what would happen then is these organics would be destroyed by crossing what I'm calling the soot line here. So we wouldn't get this pile up here. You would have just continual loss of organic molecules and thus refractory carbon carriers as these organic solids cross this soot line. And so you'd have a very different behavior and just a loss of any carbon carriers at that point. And so the soot line is something that we've been focusing on, and I'm gonna, in the interest of time, I'll finish shortly after this. But this is one of the things we've been looking at is how does the temperature structure of the solar nebula evolve with time, and what does that mean for the location of the soot line? On the right here, you're seeing a plot of temperature in the disk as a function of different accretion rates through the disk. We think that accretion rate generally decreases with age. So we would argue that the high accretion rates, oops, I have this, the 10 to the minus 7 line should be pointed to this dotted, this dashed line here. My apologies. So that's the hottest phase where you're going to have a lot of vaporization of these carbon carriers. As the system cools, the soot line may drift inwards, allowing carbon to survive closer to the star. But depending on how much material was cycled through this region here, you may have erased a lot of the solid carbon with time. And this is what we think is possibly playing a role in shaping the carbon to silicon ratio of materials in our solar system, and played a role in shaping why the Earth has lost so much carbon relative to the sun, and possibly relative to the meteorites, which formed much further out in this in the disk. So I'm going to close here. I'm happy to take questions and talk about other stuff too, if people are so interested. But what we've argued is that essentially what's happening is that rather than being condensation dominated, the chemistry of the Earth, at least as it relates to carbon, was sublimation dominated. You lost a lot of the ices at high temperature, and it's really this organic material that set how much carbon was available to rocky planets. And so how much of that refractory material was lost was going to set the abundance of carbon in the Earth. And so the bulk silicate Earth is estimated as being this abundance here, a few thousandths in terms of the plot shown here. If you add how much carbon is available, counting in, factoring in what's in the core, you can get like a range somewhere around here, a higher abundance. But what's interesting is if we go back and think about this in this plot here, the carbon, rather than acting like a 40K substance, we're arguing behaves more like a 500K substance because that's where it vaporizes. And so on the volatility trend, we would expect the bulk carbon to silicon abundance for the entire Earth to be somewhere around here if you add back the carbon inventory. And based on our estimates, based on geophysical arguments, that's pretty close to what we have estimated as being the carbon inventory of the Earth. So we think this sublimation, this condensation temperature doesn't represent a gas to solid reaction, but rather a warming of cooler interstellar media solids that would have set at least the carbon inventory for the Earth and potentially the meteorites and the planetesimals that they formed from. So that went a little bit longer than I intended. Happy to take questions or have any discussion with folks that they're interested in having. And thank you for your attention.
Okay, questions to Fred? Okay, I see clapping. It was very excellent, interesting tool. Any question?
Avi,
Yes,
hey,
Avi.
good to see you.
Hey, Fred. Yeah, great to see you too. Great talk, as usual. I was wondering, obviously, this is, I haven't actually read your team's papers yet, but something that always comes to mind when thinking a lot about these questions of how chemistry is set is what happens in a carbon-dominated nebula versus an oxygen-dominated nebula. And if you're thinking a lot about these points where different, minerals or materials condense out, obviously all of that changes. But then of course with your model of a farther soot line versus closer. Anyway, how does it all sort of work in a different chemistry C/L ratio?
Yeah, that's a great question. I mean, the argument that had been made about carbon-rich systems was that they potentially were going to deplete you of water because under equilibrium predictions, what would happen is at high temperatures, that carbon wants to suck up all of the oxygen, and then it's the leftover oxygen that goes into forming, say, water. So in our solar system, the amount of water we had was based on these equilibrium arguments was dictated by how much carbon there was. First, the carbon got its oxygen, then the water did. So the argument had been in a carbon dominated system, maybe there isn't going to be any water available in the, in an extreme. However, if what we're saying is true, then what that means is you don't have that equilibrium kind of processing. And so that carbon's coming in the refractory organics, it doesn't necessarily steal oxygen away from hydrogen to form water. So it's possible that you would have more water in such, through this pathway, if this story is correct. This opens the possibility of making water more available because it wasn't destroyed or limited due to the equilibrium chemistry at high temperatures.
Okay, so since we need to vacate this room, we will have one more question from Nick Bellery. The question is the insoluble organic matter seen in the meteorites the same as related to the refractory organics made from processed ices?
That's a great question, and we're still working to answer that. I mean, so these meteorites, as much as they've avoided any sort of differentiation, they still have been processed to some degree. They've been heated a bit. Some of them had water kind of percolate through because they've melted the ice and then created some flow. So there is parent body alteration that takes place. So one of the arguments and one of the active areas of studies is understanding when we look at the organics in these meteorites, what were the original pieces that were present during accretion that led to the building of what we're seeing here in the meteorites themselves. So there's some processing there that we're not seeing an exact record of what was floating around in the ISM.
Okay, so thank you. Let's, Ilaria, do you have a quick question? I think we have a few minutes still.
Okay, yeah, thank you very much, Fred. This was very interesting. And I'm sorry, I also joined later. So you might have said that, but I was wondering, what would be the amount of carbon to silicate in the Earth if you would take this condensation model, but then you would also consider the dispersal of essentially a lot of the carbon CO, right, from the inner part of the disk. Would it be different, a different prediction?
So you're saying if everything was equilibrated and there was just CO floating around in the disk, would we have gotten carbon?
And then you would disperse basically the CO. What would have been the carbon to silicate ratio in the Earth? It strikes me that, right, in the figure you show, the carbon to silicate ratio has a kind of radial dependence as well when you go from Earth and satellite chondrites and carbonaceous chondrites. So just a curiosity.
Right. Yeah. No. I mean, if we were to follow equilibrium chemistry perfectly and exactly, I would say that we wouldn't have any carbon on Earth. Because it would all have been CO, as you said, in the gas. So unless there was some primordial atmosphere and we retained a little bit of it, I think we'd have a very low carbon abundance on Earth. The fact that meteorites contain some organics and everything is telling us that, you know, we didn't destroy everything. Everything didn't go into CO in the gas phase, at least in the inner part of the solar nebula. So yeah, I guess the only carbon we would have would be the little bit that pollutes the Earth over time from other sources.
And that would not be enough to come to the value we have.
Right.
Okay, thanks.
Hey, Sebastian.
Last question, Sebastian.
Hey, Fred. Good to see you. Sorry, I joined super late, so you may have said this. I was wondering. So I'll ask a serious question first. So the physics that sets where the soot line is during the disk phase is different from what determines where the habitable zone will be later on, right?
Yeah.
So I was wondering, have you thought about whether sort of the distance between the habitable zone and the soot line, whether it shrinks or gets bigger as you go to lower mass stars or M dwarfs or something like that?
Yeah, that's a great question. I have thought about it. I haven't done a lot with that, but I think, you know, one of the things that's important is if we're right, you know, we do expect a variety of outcomes because, you know, the dispersion we see in, say, mass accretion rates or what have you for different stars is pretty significant. So those that have very rapid high mass accretion rates early on, we would expect to be, you know, probably forming carbon depleted planets. Whereas those that may be from a more extended disk where it's lower mass accretion rates may preserve that carbon more readily. So that's something that we want to spend some time thinking about.
Yeah, that sounds good. But I think sorry, I'll stop.
Okay.
Well, I'll have a question too, but I'll ask them later by email. Okay,
I'm happy to answer any questions.
Sebastian, you please feel free to write email to Fred about the question. Thank you very much for your excellent, very interesting talk, Fred. And let's you can unmute and let's thank Fred again.
Good to see you all. Take care.